Okay, welcome everyone to this long-range colloquium. My name is Eliška Greplova and I will be host and moderator today. Just a quick introduction if this is your first time joining us, but I see a lot of repeated visitors in the audience. Virtual Science Forum is an open, collaborative, and volunteer-run initiative to facilitate online scientific seminars and conferences. If you would like to join our effort in any way, suggesting speakers, organizing conferences, joining the organizing committee, please go to our website. I posted it in chat and I will post again in a few minutes. All our content is available on GitHub and in our YouTube channel. Let me also take this opportunity to advertise a new format that we are introducing now. We call it Virtual Science Forum Speakers Corner. And this is an event format where you can invite yourself or you can just invite colleague who has anything interesting to say. We aim for this to become like an archive for talks. So whenever you have a talk, you can just register on our website and we take care of all the overhead. We set up the Zoom meeting for you, take care of the advertising, and all you have to do is to show up and advertise your talk at your own institution. About Q&A, use the raise hand option of Zoom in the participant panel that you see at the bottom of your screen. And I will be moderating, and if I see someone raised hand, I will interrupt the speaker and let you ask your questions. So let's move to the colloquium today. We have Natalia Ares from the University of Oxford. Natalia is well known for her work on quantum devices like spin qubits and carbon nanotubes, but amongst other things, she also pioneered efforts to use machine learning to automate methods for tuning and measurement of quantum devices, which is something that she will also discuss with us today. So very warm welcome, Natalia. Thank you for joining, and please go ahead, share your screen and start your talk.
Well, thank you so much, Eliška. This is really a nice, let me share, there we go. This is a great opportunity for me to tell you about what we are doing. So yeah, thank you for giving me this space to talk about it. So my talk today, it's called Measuring and Tuning Quantum Devices Faster Than Human Experts. And let me motivate that title. So we are focused in creating and building a technologically relevant number of quantum devices. And for this, there are different material systems with promising characteristics. These are superconducting qubits, they are ion traps, they are semiconductor qubits. And at the same time, we are seeing real breakthroughs in computer science, like algorithms beating the best players in the world of Go, algorithm playing StarCraft, and also even writing complete texts from scratch. So in the light of these kind of two very exciting activities, one has two questions, right? One is, well, can actually quantum technologies help us take artificial intelligence further? And the other question is, well, can artificial intelligence, and in particular machine learning, help us in the scalability of these quantum circuits? And that's the question that I'm going to focus today on. So the question is, then how can artificial intelligence, and in particular machine learning, can help us in the scalability of quantum circuits? Well, whatever the qubit realization, typically we have a device and we want to take it to the operation point in which it acts as a qubit. And that process has requires tuning and characterization, and typically it has like different stages. First, we do like a super coarse tuning, a coarser tuning, and then a more fine kind of tuning, and each of these stages basically, in each of these stages, what happens is that, well, we have a few parameters, and we can measure in order to evaluate if the change in parameters we did was helpful. And we have this kind of feedback between the measurement and the search for good parameters. And even when we have an operational qubit, we want to have the best qubit that we could have. And then again, this tuning and characterization and evaluation process starts. But then this is a very time-consuming task, even for experts in each of these devices. So the dream is, can we really have an artificial intelligence to which we say, well, here you have a device. Can we push a button and suddenly have the best qubit you could ever have with that particular device? That would be really something that could help us go from one device in which we have to do all this work to have millions of these devices. And in this way, we can really unleash the potential of these quantum circuits in more complex architectures. Okay, so today I'm going to focus in semiconductor spin qubits, but most of what I'm going to say actually doesn't care, and we can actually take it to completely different material realizations. So in a semiconductor spin qubit, typically we encode the qubit in a single or double or triple electrons, and to do that we have to isolate those electrons. So we can do that by engineering an heterostructure of semiconductors and confine the electrons to a two-dimensional electron gas, as you can see here. But then you have to also create like little paddles in which these electrons can be confined. So these are quantum dots. And you can see that we can do that by depleting the 2D with gate electrodes to which we apply a gate voltage. And we can measure single electrons tunneling in and out of these quantum dot devices when we apply a bias. And we can measure, let's say, a current that flows through the device. So here you can see some micrographs of single and double quantum dot devices. And because we have to reduce thermal excitations to isolate single electrons, we have to measure these chips at very low temperatures. So here you can see one of the chips and sample boards that we measure in a dilution refrigerator at around 20 millikelvin. So this is a photo of one of our dilution fridges at Oxford. And now let's look at it from a very kind of machine learning perspective and say, well, here, let's just identify which are the parameters and what are the measurements. And the parameters are going to be these gate voltages or bias voltages that we can change. And the measurements we can perform can be measurements of current. There are other ways to measure these devices, like faster ways, and like, for example, with reflectometry, in which we have a radio frequency signal that we measure. But current is the one that I'm just going to focus on today, just to pin it down. But, and what kind of measurements do we do? Well, we can measure the current as a function of one gate voltage. We can measure the current as a function of two gate voltages. We can measure the current as a function of bias and gate voltage. And we would see different structures. And some of them are characteristics of single dots, for example, these diamonds here, or these bias triangles, which are characteristic of double dots. So from the machine learning point of view, we have these parameters and we have these measurements. And this is like the core of what it's going to be the automation. So there has been fantastic work already in semiconductor device, quantum devices using machine learning for tuning and measurement. And this is not an exhaustive list, but you can see that the years of those works are all, 2018, 2019, 2020. So there is now a big effort that has just started to take to make the most of this opportunity to use machine learning to really have the best of our semiconductor qubit devices. But let me tell you where we are at. So my group, and for this, I have divided, again, the different stages of tuning and characterization. And I have also divided the classical machine learning and the deep learning type of machine learning. So the idea is that in the classical machine learning, that there are problems that are a lot better suited for classical machine learning, some problems that are a lot better suited for deep learning. So you can see that, for example, so for super coarse tuning, we started with classical machine learning and we went to deep machine learning a bit and come back. So our idea is to use what the tool that better suits our problem. So just to, these are some of the papers that are out there from my group. You can find our algorithms in GitHub, and I encourage you to go there and take a look. So, but let me start with this one here, our approach to super coarse tuning. So the problem is, what is the problem that we have to solve here? Well, the problem is that our devices act like transistors. So for most of the parameter space, either we have too much current flowing through the device, not very useful for qubit operation, or we have no current at all. Again, not very useful. So what we want is to actually find places in the parameter space where we have single electron transport. And these can be a single or a double quantum dots that are formed in the structure. But we have to find those places first. And this is why it's super coarse. In the beginning, we just have a transistor, and we have to find these particular operation conditions in order to even think about isolated electrons. Now, these are two gates here. Now, if you have three gates, you can see this is just an illustration, it's not a measurement, but you can see now we have like some sort of surface that separates areas of a lot of current and areas of no current. And again, we have to find in this surface the places where we have the places in parameter space where we have single electron tunneling. So just to give you an idea of how big this parameter space is, if we have 4 gate voltages, and let's say we have a range of 4 volts, and the features that we are looking for that are signatures of single electron transport are in the order of millivolts. So that makes 4 times to 10 to the 12 points to explode. And if you're measuring at, I don't know, 100 points per second, that gives you something like 127 years. It's huge. Of course, we don't do this. We have some tricks and things to find these regimes. But this gives you an idea that it's really a huge parameter space. And it can be 4 gate voltages or 8 gate voltages. And now this surface becomes some sort of hypersurface in a multidimensional space, which is huge. So here you can actually see one of these hypersurface. This is a measurement here, and these are just 3 gates out of 8. But just to show you how it looks like, and here where you can see darker regions is where we have single electron transport. So now the question is, how do we explore very efficiently this hypersurface and completely automatically? So the problem, it's a bit like we don't know about the hypersurface because we never measured the entire hypersurface, just to show you, but that's not something we do because it's very expensive in terms of lab time. But what we can see is that we measure a tiny portion of the parameter space, and we have to, well, and we check there if we see single electron transport, and we have to basically check where we can, if we don't find it, search for another area and start again. So this is what our algorithm is going to do. The problem is a bit like the multi-armed bandit problem. Why? Because, well, basically we have a gambler that is our experimentalist, and the objective is to have to maximize the reward. So in the case of the experimentalist, is to find the places where we have single electron tunneling. But the question is, where should it look? And in the case of the gambler, the question is which machine should this gambler play next? Because as you can see, there are machines that have a very high current success rate, but there are machines that the gambler haven't tried, and maybe they have even higher current success rates. So this puts in the picture what is called the exploration versus exploitation trade-off. So, we can exploit the fact that we know the current success rates of one machine are high, or we can exploit new machines that we don't know about. And the same is going to be with the hypersurface. We can exploit the fact the successes in finding some single electron transport, or we can explore completely new areas that might be a lot better. So what does our algorithm do? So just to explain this, I have pictured the hypersurface in 2D. So here you can see the pink is places with current, and the blue is places without current in the parameter space. But the algorithm doesn't know this, right? The algorithm doesn't know where the hypersurface is, because you just put the device in the fridge. So what the algorithm does in the beginning, it doesn't know anything. It just takes a measure in a random direction in parameter space. And when it sees the current has dropped significantly, it says, oh, okay, this must be the edge of the hypersurface. So this must be a point in this hypersurface. So it stops there. And what it does next is to explore a bit the boundary in this hypersurface. So it does a small measurement of current as a function of the gate voltages in a given direction. And here, the algorithm can have two possibilities. Either it measures the current as a function of gate voltages and it sees nothing, or it sees Coulomb peaks. And Coulomb peaks are evidence of single electron transport. So, okay, with this information, now the algorithm can create a model, because after a couple of iterations of this, we have a couple of points where we know we have a couple of points in the hypersurface, and we know which is the probability of finding peaks in that along that hypersurface. So we would create the algorithm would use a Gaussian process to create a model of that hypersurface, and also a model of how probable it is to find Coulomb peaks in that hypersurface. So here you can see these green and yellow points are evaluations of the hypersurface, and this green and yellowish line, it's a model of the hypersurface itself. And the green and yellow, what is telling us is how probable it might be to find these Coulomb peaks in the hypersurface. So now we have a lot more information that we have started with. So now we won't do again these big searches, these big ramps of current as a function of gate voltages, because that's expensive in terms of lab time. And because we have a model, then now we can explore points that are in the hypersurface that are promising. So now we would choose one of these points in the hypersurface, a new point, and we would explore in a lot more detail around, and we would see what we find there. In this case, what we were looking for were features that were corresponding to double quantum dot type of device, of transport feature. So you can see now, if we do a measurement of current as a function of two gates around that point, we can actually see that the algorithm has found double quantum dot features. So this is the way our algorithm works. Let's concentrate a bit more here in the model. How do we create this model of the hypersurface?
So yeah, maybe, sorry for interrupting you, we have a question from Anton.
Yeah, that is all.
Yes, so I wanted to understand a little bit of the details. So first of all, can you please explain why do you call this object a hypersurface if it really has a finite volume? So Coulomb blockade peaks occur in a volume in the parameter space.
Well, so indeed, you're right that, so we call an let's say the hypersurface is what we define as when the current starts dropping, and we know that something might be happening there. So we know that these features would happen in some kind of belt around, you see, this hypersurface. So as you can see, once we identify where the hypersurface is, we do measurements that actually go inside or around that point. And this is because we expect to see these features around where this hypersurface is, let's say. It's just a way to tell the algorithm that that's a promising kind of place to look for these features. So let's say the hypersurface is just a way to tell us that we are at the point where we might find single electron transport in its surroundings, let's say.
Mm-hmm. And can you be more specific when you say what you call single electron transport or peaks? Because in a single point you just have a single value of current. So what exactly are you talking about?
Yeah, so you see here, so this point here is the point where we say, okay, that's a hypersurface, that's a single point, that's a single coordinate. But in order to know what's going on and to see if that's indeed a promising kind of place in the parameter space, we have to do a measurement of current as a function of gate voltage. So that's where we open again, let's say, the dimensionality from point to trace. So here you have to do a trace around or in the vicinity of that point and see what's happening with the current as a function of gate voltage. So there is where you leave the kind of point to kind of go to a trace. And because this, in order to distinguish if you have a single dot or a double dot, you have to go to even higher dimensionality. So here you can see that we took actually a 2D plot let's say the current as a function of 2 gate voltages, because that's how we identify features that we know are corresponding to the double dot regime. If you were to have a triple dot or a quadruple dot, you would have to choose kind of a plane to look at, or some other smart way to kind of to identify those features.
All right, thanks.
Hi.
Thank you. Yes.
Sorry, just a follow-up question. These measurements are happening not in simulation, but actually in the lab. So exactly. You have somehow a Bayesian method to explore this parameter space, but you are continuously getting feedback from the experiment.
Yes. So, well, I don't know if I would call it Bayesian in the sense that we don't have like an acquisition function, but it does have a Gaussian process that is guiding the measurement. So indeed, this iteration of the algorithm is happening in real time, and we can count. We can kind of say, okay, run, and we count at the time it takes to come up with successful, let's say, coordinates that we think are really good. So yes, so that goes in real time. And the nice thing about this algorithm is like it's not computationally expensive, which means that our bottleneck here is the measurement time, and there are ways to speed up measurement time as well. So at that point, if you manage to speed up the measurement so much, you would have to at some point speed up the algorithm as well.
Okay. Yeah. Thanks. Yeah.
Great. Well, thank you for those questions, because it does help me to kind of explain what's going on. So yeah, so let me go back to the model of the hypersurface and how we can, have this model. So, well, let's say that we have the hypersurface here. The real hypersurface is this red line here. But the algorithm doesn't know that because it hasn't measured it. So what we have is some sort of prediction here in blue, and that prediction has some uncertainty. Okay, so these are like the shade, the blue shade here, and we have some evaluations. We have some places where we have actually measured the hypersurface. So these are these black points here. So now in the next iteration, what we have to basically find is we would take another evaluation, but we have to ask ourselves which is the evaluation that would help us minimize the uncertainty in which we think is the hypersurface. And this is how our algorithm would choose the evaluation of the hypersurface. Now there is one more issue here, and is that the hypersurface is not like a hypersphere, because the topology, I'm not sure if with Anton present I should use that word at all, but let's say the topology of this hypersurface, it's you know, very bumpy. So how do you guarantee that you're sampling that hypersurface homogeneously? And the way we found to do that was to actually simulate Brownian particles in this kind of predicted hypersurface. And whenever these particles hit this, you know, the predicted hypersurface, we choose that point as a coordinate to evaluate. Then, of course, in the beginning, it's just this random, you know, these Brownian particles. Then we just use these as candidates, and we choose this kind of these candidate coordinates depending on what is the uncertainty that it would give us in the evaluation of the hypersurface and the probability of finding peaks. So that's a bit how, that's like a very brief idea of how the modeling actually works for the hypersurface. So you see the algorithm gets more and more information, and in the light of that information, it can make smarter decisions. So this is what is really cool about this. So now let's see the performance. So to check the performance, we have compared the number of the average number of successes. And by success, I mean that it finds, it makes a 2D plot like this one. Sorry. That completes a measurement that it's labeled a posteriori by a human as corresponding to double quantum dots. And that's why it's average, because we have, in order not to be biased, we have asked a lot of people to actually say if they think they would consider that a double quantum dot. Although in the ones that are super clear, we all coincide, but you would be kind of surprised of that sometimes there is no complete, there is no full agreement on this. So that's why we ask a few people, and we use an average number of successes instead of a number of successes. We have plotted that here as a function of time, both for a random search of the hypersurface and our algorithm. And what you can see for the random search is that sometimes you are lucky. And indeed, by randomly searching in the hypersurface, you hit indeed a measurement of exactly what you're looking for. But that happens rarely. And you can see here that we had a success after in the order of 8 hours. But our algorithm, of course, it's smarter than that. And we have several runs here that you can see with several successes. And in this way, we could show that you can tune a double quantum dot device, and this is an 8-dimensional parameter space under 70 minutes. And again, we have asked people in the labs, well, how long does it take you to, you know, reach this tuning kind of stage in the lab? And we have concluded that our algorithm our algorithm performance is superhuman. And well, every now and again we find that, you know, very kind of you know, we still have our pride, and we want to win and tune a device faster, but we haven't managed yet. The algorithm still wins for the moment. And there is one very attractive thing about this concept of the hypersurface, because it allows you to think of device variability. And why? Well, because once you have an idea of how the hypersurface of these devices looks like, you can, if you have 2 devices, you can compare this hypersurface and think, what is that makes them different? How different are these hypersurface? And that's why, because they are different, is that we have to use these kind of smart algorithms, because we can't predict how this variability actually it's going to look like. But with let's say an idea of how the hypersurface looks like, we can quantify the variability. So for example, if we have a device 1 and a device 2, and we have the 2 per surface, we could kind of try and find a transformation that goes from device 1 to device 2. So for example, here you can do it just simply with, I mean, just to show you, just in 2D, you can just transform one input surface into the other and find the matrix that does this transformation. So that's what we have done, and we have then characterized, let's say, different devices. And this is the matrix that takes each of the gate voltage into each other in this kind of 8-dimensional parameter space. And as you can see, these 2 per surface are quite different. But something that you can see as well, that if you thermal cycle a device, let's say if you heat it up and you cool it down, and you heat it up and cool it down again, the only thing that seems to happen, you see the matrix is rather diagonal. So what it seems to happen is that the device can, like the upper surface, just scales. And this is something quite interesting, because it does tell you what is happening with the device and why it changes from cool down to cool down, or from a device to another. So I think this is an interesting way to actually quantify variability in devices. So as I was mentioning before, here the bottleneck, this is an algorithm which is quite classical in the sense that it doesn't use any type of neural networks. So and it's quite fast. And again, the bottleneck is the measurement time. So there are different ways to speed up measurement, as I mentioned before. We have also investigated ways to kind of use machine learning to speed up measurement. And I can tell you a bit about it now. And you've seen that I have placed this kind of algorithm a bit in between classical machine learning and deep learning. And the reason is because we are using both here. And let me show you how. So you will see, like, the let's say deep learning part of this algorithm has to do with encoders and decoders. So for those of you that are not super familiar with this is how, for example, image recognition happens. We have a high level representation of a cat, let's say this figure, and we want a high resolution image of a cat, for example, and we want a higher level representation of that. So let's say that it has ears and it has a tail, and in order to go from this high resolution image to a higher level representation, we need basically weights that let us map one layer into the other. And this is what an encoder would do. And this is just not one layer, it's many layers. So in some senses, well, it is just a composition of functions, each of which has weights and some other parameters that you can add as well, that are learned in a training process. So here we need a training stage in order to learn these weights and find a way to actually go to this higher level representation stage. But you can do also the following, which is these deep generative models. So in deep generative models, you have the high resolution image, and what you have the higher level representation, and what you want is to kind of recover the high resolution image of a cat. And this is again, a decoder is a neural network that you have to train, and you will learn those weights that allow you to go from one layer to the other. So, so this is what we use, and let me show you how. So these deep generative models then can actually come up with, let's say, pictures of a cat or pictures of people that are not real, as you can see here, although they look real because they have been trained on, in this case, celebrity faces, so they kind of look like real celebrities, but they are not. It's this decoder that it's bringing this kind of higher level representation into a high resolution image. So how we use this in our devices? Well, if we have a low resolution measurement in our device, we can just ask the algorithms to come up with ways in which these deep generative models to kind of dream up and come up with high resolution images and high resolution measurements. And you can see here a few of the ones that our algorithm came up with. So this is already very powerful because with a low resolution image, you can actually have a pretty good idea of how our device looks like using these deep generative models. But you might want to go one step further and say, well, actually, well, these three kind of reconstructions or images the algorithm came up with are not, for example, are not identical, of course. And here, for example, this diamond is closing, but it's not closing here. And I want to kind of differentiate these two pictures without having to measure the entire image. So here is where the classical machine learning comes. So if we have a partial measurement and there's a trace here that we want to know about, but we don't, something we can do is, well, take just that information, that trace of all the reconstructions that the algorithm came up with. So these are all probabilities of how that measurement might look like. So here you can see the current as a function of gate voltage, so this trace here, but for the different reconstructions that the algorithm came up with. And now I have highlighted one in yellow and one in blue because they are very different. So now the question is, if you have to make another measurement, well, you better do it here in X1 rather than in X2, because X2 won't let you differentiate between the different reconstructions. So in that way, we can create what we call an information gain map. How much information would you gain by measuring a particular part of the diagram? And we can do this in for the whole measurement map. So we can have an information gain map or an acquisition map. So our algorithm starts with an initial scan, which is very low resolution. Asks the deep generative model to come up with ways in which this measurement might look like, creates an information gain map by comparing these maps and seeing where they differ the most. And then in the light of that, it makes a decision of where it's going to be more informative to measure next. It measures that particular point, and then in real time updates the guesses, the reconstructions that the algorithm has made in order to fit with this new information. And in this way, we can significantly reduce measurement times. So here
we have
yes?
another question.
Yeah, sure.
Please go ahead, someone else. You're muted.
Oh, sorry. Yeah. So my question is basically, what guides your reconstruction process for the deep generative model? So for example, if you have a generative adversarial network, it needs to be trained on some data that tells you that this you are basically solving the problem of super resolution. You have a few information about an image and you are trying to do in painting or filling it. But what is to say that it should paint it with, you know, these triangular shapes? So how do you train it in some sense?
So we train it with measurements and we train it with simulations. In the end, simulations are enough, but we have also included a few measurements, and we don't have many because they are expensive. But we have included some measurements in our training set because we have realized that it helps a lot. Just a few measurements help a lot in the training set, because then the algorithm it's more has seen, let's say, noise. And although the simulations, of course, you can simulate the noise and you can do all sorts of tricks and augmentation of the simulations and also of the measurements. It's kind of helpful to have some real and there's a paper actually about you know how it impacts performance to have real real measurements in your training set. We've seen it's important, and that's why we have included some of these measurements there.
But for the simulations, for example, I mean, I don't exactly know how this data is, but when you generate this data, do you have some kind of an analytical model for it that generates these surfaces?
Yes. Yeah, so we have an analytical model, in particular for this Coulomb diamonds is quite easy because it's just what we call a constant interaction model. It's a capacitive model, so it's very easy to do this kind of model. But of course, if you have a more sophisticated kind of measurement, a measurement which requires a more sophisticated model, then of course the simulations would be expensive as well.
Okay, thanks.
Welcome. Okay, so just to show you how it actually works. So here you have the measurements the low resolution measurement that we have performed, but here the pixels are separated so that we can fill it in with more measurements. And here you have an acquisition map that it's how informative is to measure in each point. And you can see that the points that we have measured are in black. It's not so informative to measure where you have already measured. And you can see that the algorithm tends to fill the outsides of the diamond. And the last thing it does is actually fill the diamonds. It's because inside the diamonds, the current is 0. It's flat, typically, which means that there is not much to gain in terms of information. All the diversity of this data has to do with let's say, the outside part of the diamonds. And this is an emergent behavior of the algorithm just because it's looking for information gain. And this is what I was just trying to bring up just then, that because it's just you just need a training set. It actually works with different sets of data that look very different, or simulations that look very different. Here you can see that the current is flat in this big part of the current map, and you can see that's the last thing it does. It's first takes the places where the information gain is higher. So the question, of course, I'm just showing you the algorithm taking the full measurement just for completeness, but of course the question is, where should you stop measuring? And that really highly depends on what you're looking for. But one way to think about it is that you can say, well, I'm going to measure the unmeasured current gradient over the total current gradient. And this is what we plot here as a function of the measurements. And if you do a grid scan, which is what we typically do in experiments, well, you would have this black line here. If you were to use our algorithm knowing exactly how the current map looks like to begin with, which is something that you don't, you would have this green light here. So that's the optimum. And the blue line that you can see, it's how our algorithm performs. So it's not too far from optimal. And well, the question is, where do you actually stop measuring? Well, you can say, well, when I'm gaining information at less rate than the grid scan, I would stop. And that's what we have chosen, and that point is here. But you can see that depending on what you're trying to see, you might stop a lot sooner. So that's again an open question in terms of how much time would this save.
So
now
we have an additional question from Anton.
Sorry, it's a rather quick question. And this is also something that we actually realized when studying the work. So if I understand correctly, the measured gradient versus unmeasured gradient refers to points on the highest resolution map, right? So say if I take the same data and I double the resolution, then by this measure, I would like have half a quarter of the information. Wouldn't it be a more accurate metric to get the data that you know and do, for example, I don't know, a linear interpolation, so the quantities are comparable?
Well, I'm not sure exactly what you mean, but of course here the resolution in the end, there is another thing, which is how many measurements. So here, let's say, we are taking batch measurements, which is that we decide a batch of points that we're going to take, and we take them, right? And in the end, the resolution of your figure and the size of your batch that you're taking measurements would also be something to kind of balance, right? Because of course, well, that would really depend on how much time you gain, on when do you do the calculations, or with let's say how coarse is your measurement would also depend on which is your choice of batch, if you want, right?
Right. So what I mean is the following. Say, imagine I take the image on the right.
Yes.
Say, there I would say, regardless of how many more points I add in between already existing ones, I already know everything there is about this figure. There is no new information. So
exactly. Yes.
does the metric R of n depend on how many points I have, or I have, like, say, if I allow myself to measure 4 times more points, and I measure only the points that are on the image on the right, does the metric say that I already measured essentially 100% of the information, or not quite?
I think, well, I mean, in the end, is the total current gradient, because you're measuring in the end the derivative, right? So you're measuring when it changes. So I think it's true that because you're measuring the derivative, probably you're dependent on the resolution here. Yes, so it would be something that you would have to normalize against, I guess.
All right, thanks.
No? Yeah, I'm not sure how you, but yeah, it's resolution dependent. So you would have to kind of make a decision about it. And of course, you don't know the total current gradient when you start, which is something that you can estimate and predict, but you don't know it in advance. And that's what we have an uncertainty bound here.
Yeah, right. All right, got it, thanks.
Okay, so this work now sets up the kind of scene for this paper that we just put in the archive, because this is very helpful to kind of reduce measurement times, but it's not as good for let's say tuning when it becomes a lot finer. And the reason is that now we are, once the device is, let's say, coarse tuned, we want to focus in particular features that are typically isolated. Let's say that the landscape of features is rather flat, except for that particular feature that we are looking for. So there is nothing to, let's say, guide the algorithm in terms of where it's going to have this information in. So for this, we have used a deep reinforcement learning approach. So deep reinforcement learning, it's what, for example, DeepMind has used to play games like these Atari games, like Breakout. And basically, there is an agent that has to take, let's say, decisions. And what this agent wants to do is to maximize a reward. And it doesn't have to be the immediate reward. It can be a long-term reward. So there is a balance between the immediate rewards and the long-term rewards. And that's what the what these deep reinforcement learning algorithms can do. So what do we want this algorithm to do? Well, for example, if you would have a current map where we have already used our super coarse tune algorithm to find some features that look like double quantum dots, but we don't want to measure this completely current map, that's expensive. And now we want to really navigate to this very, in a finer tuning, we really want to navigate to these very tiny islands of current. And as you can see, there are a lot. There is a lot of flat landscape around them, so there is a lot of zero current around them. So what we want the agent is to start somewhere in this map, and we won't know where exactly, because our coarse tuning algorithm would say, well, around here there is a promising place in the parameter space, and we would want this agent to actually go searching for these bias triangles, which are the features that we are looking for, that are like islands of current. So here you can see, so this is what the agent in our deep reinforcement learning algorithm sees. So it doesn't know where it has to go. It starts somewhere. It knows that somewhere it's going to find these features, but it doesn't know exactly where. And what it can do is go up, down, left, right, or in diagonal. And you would have to navigate to these particular features. So here you can see an example of this. It has actually started here, where is that corresponds to some position here. And you can see that it goes directly to find these little bias triangles. So this is very efficient, because now it has just measured a few blocks of this current map, and it has found these features very efficiently. So that's exactly what we wanted. And let me show you how this algorithm looks like. So the algorithm starts by making just a measurement of current as a function of gate voltage in extreme positions of the parameter space, just to normalize the current, just to know where it's going to be higher current and lower current, what's going to be the highest current and the lowest current. So it starts with this current trace, which is quick because it's one-dimensional, and then it would start. It would start in a given block, and in this block, instead of measuring the whole block again to minimize measurement time, what it would do is take randomly a few pixels in the block, and then it would divide that block in subblocks, in 9 subblocks. And it would calculate the mean and the standard deviation current in each of these blocks. Why it's doing that? Well, the idea is that with that information only, it would be able to distinguish if it's promising, if that block is promising or not. So how does it know? Well, with that vector of mean current values and standard deviations, it would do a pre-classification. And this is just a neural network that would decide if it's the standard deviations and current values corresponds to what typically we see in single electron transport regimes. If it does, then it would do a measurement of the block, and it would feed it into another neural network to classify. And it would ask itself, is this a bias triangle, which is what I'm looking for, or not? If it is, then we are all happy. First block, it worked. If it didn't, or if the pre-classification said that it was not corresponding to single electron transport, so then the algorithm would go into the deep, let's say then the agent would have to decide what to do next. And that's where the deep reinforcement learning part comes, because from this vector of current values and standard deviations, it would decide if to move up, down, or diagonal in this current map. So it would move, it would find another block, and again would take random pixels, and it would decide what to do next. So this is how our algorithm moves and navigates these current maps. So here you can see 2 examples. So this is the GIF that I showed you before. This is another example of a different current map that it has navigated here from the blue to the red. So it doesn't really matter where you start, it always navigates to these bias triangles. And again, in order to check the performance of our algorithm, we have compared our approach with a random agent. So the random agent here has exactly the same, let's say it has everything in the algorithm. So it has everything except this deep reinforcement learning agent. It's just a random agent, but it still can classify and take fast measurements. So it's a rather smart random, but the decision is random. So and so that's the comparison here between pink and blue. And what you can see is that the deep reinforcement learning agent lands in bias triangles a lot more times. So in the histogram, it has the higher values and then drops quickly, while the random has a longer tail. And we can see this in the different current maps that we have tried. And you can compare the numbers of block measurements between the deep reinforcement learning and the random, and you can see that the random in average takes a lot more blocks to reach the bias triangles, and therefore it's lower in average that the deep reinforcement learning. And with this, basically, we just extracted the deep reinforcement learning agent to see what is the advantage of this agent. And as we can see, there is advantage in having the deep reinforcement learning part of it. Okay, so now we have, so we didn't know in the parameter space, we were in the dark. We found a nice place where there was a double quantum dot regime. We want to measure fast. We can do it in the coarse tuning with this algorithm here. We can do it in the finer tuning with the deep reinforcement learning approach. But once you land the bias triangles, you have to get them right. And this is what this work is about. So bias triangles in textbooks look like really nice, sharp pair of bias triangles. But when you find them in a device, typically they look more like a blob. And then is where you go with all the gate voltages, trying to get the shape right. And the reason is that because we know when they are sharp and they have particular features, we have a better chance to see and to operate this device as a qubit. So this is a very important part of the tuning, and it's very time consuming. So here we have developed an algorithm that can do it automatically. And this has a very interesting part, which is the part that, well, what actually makes a nice bias triangle for qubit operation. So, well, let me show you how our algorithm works. So, oops, okay, there you can see now our algorithm is tuning other gate voltages to kind of get these bias triangles a lot sharper. And so here you can see that it went from a blob to a sharper bias triangles, which we typically identify again with a good qubit operation. But that's expertise basically. So let me show you how the algorithm actually works. So we come back to our encoders. So what we want to do, we have a high resolution image of our bias triangles, and we want to encode it in a higher level representation in a latent space. So what our algorithm does is with this encoder have produce a latent vector, so produce a higher level representation. And in our case here, it's 10-dimensional, this higher level representation. But we just to illustrate it, we have plotted it in 2D, and we have like reduced the dimensionality just for illustration. And now in this latent space, we say, well, the bias triangles that we actually think that are promising might be in some particular place in this latent space. So here, for example, these, I would say that they are very nice bias triangles, and I think these have really, they might be promising for qubit operations. So these are my, I would like these bias triangles to look more or less like that. So now, if I have a new measurement of bias triangles, I can encode them in this latent space. And when I do, for example, in example 1 and example 2, I can see how promising, let's say I can measure how promising they are in terms of how far they are in this latent space from the target. So this would give me a way to score them, to say how good they are automatically. So in this way, we can produce a score, which is, well, how far am I in parameter space with my example from the target example? And depending on that score, I can change my parameters, which in this case are the other gate voltages, and repeat the process until my bias triangles look very much like what I'm looking for. So this is what our algorithm does. And now the question is, how do we choose the other gate voltages to basically produce a new image and score it? So this is a very simple way to find, to produce, let's say, different images and different parameters. It reminds me, I'm not sure why exactly, but it does remind me of this episode of Black Mirror, Bandersnatch, in which you can choose you know, what the character does, and then you know, some paths, in some paths you die or something, and then you have to you go back to the point where you make a decision that might have led you to to death. Well, it has some analogy, because you start with some gate voltages. In this case, we consider 3, let's say B3, B4, and B5. And the algorithm has to choose what to do. It has measured a score, and it was to improve that score. So the options that it has is change B3 to a greater value or a smaller value, and the same with B4 and B5. So randomly, it chooses one of them and checks this and goes again to check what's the score of this new measurement that this change has produced. And if the score improves, then it accepts that change. It says, okay, this is good. So I'm going to start from this new vector, in which I now start from this voltage, which is reduced by this delta. So this was a good change, so I accept it. But now it has to choose again. And the only thing it cannot do is go back, because it has accepted the minus delta B3. So it wouldn't be good to do plus delta B3 again, because it would just undo the previous step. So, okay, it can choose randomly again. And let's imagine it chose that plus delta V4. But then it produces a measurement, and let's imagine that the score actually worsens. And then what we do is reject this change, and we choose another change randomly from the other set that we have. But let's imagine that we went through all these changes and none of them improved the score. So then we kind of have the situation in which we reject all the changes in gate voltage that we can possibly have. We have no way to go. So like in Bandersnatch, when you die, you go back to the previous state before you have accepted the change that led you to that situation. So this is a very simple model, just to choose the gate voltage to change next. This can get a lot more sophisticated. One can use Bayesian optimization for this, for example. We have observed that this works rather well, so we didn't want to overcomplicate it, but this is the way, yeah, that one can do it. So here you can see for our algorithm, the score as a function of the iteration. Something strange here is that we want the score to go down, which is typically not the way we think about scores, but there we go. So we want the scores, the lower the score, sorry, the lower the score, the better. And here you can see the score as a function of the number of iterations for 4 different bias triangles that we have fed our algorithm with in real time. And we see that with just a few iterations, the score goes down a lot. So with very few iterations, we do the fine tuning automatically. And we can kind of map what our triangles did in gate voltage space. So the circles here are the starting points, and the crosses there are the final points. So you can see that in some sense, that they are making a trajectory in gate voltage space that improves their score, and in some sense they are kind of converging to a given set. So this is again, this leaves us at a point where, okay, we have now from scratch have a very nice pair of ice triangles where we can operate a qubit. So now we are working as well in the optimization of the qubit and the measurement of qubits. And here we this is work in progress, but we have taken elements of this paper here again, because for example, in the qubit operation, we have to again perform evaluations and characterizations of the qubit, and those are time consuming. So again, we can use tools that we have already developed, like this information gain, for example, here, to acquire data of the spin-up probability as a function of the microwave pulses and the pulse duration, and this might allow us to tune our qubits a lot faster. So that's where we are heading. So with this, let me now summarize. I showed you, let's say, how we can do efficient quantum dot device measurement and tuning using machine learning in different stages of the tuning going towards qubit operation. Where we are going next, as I say, optimize these qubits. Let's continue this path, and also start tuning larger quantum circuits and more complex architectures. So this is where we are heading next. And well, there is other lines of research that my group looks at. These are recent papers on each of these. One has to do with faster measurement. So what I was saying about using radio frequency circuits to measure faster. So this would again help also the fast tuning of and characterization of devices, and as well how to understand the thermodynamics in these devices in which fluctuations are important and quantum effects are important as well, and how the laws of thermodynamics kind of actually have to be revised in that picture. So happy to talk about those as well. And well, let me thank my group, which is fantastic, and my collaborators, which are many as well, and really great. Nothing would be possible without them. So thank you.
Thank you so much, Natalia, for this super interesting and clear talk. Now we are virtually applauding. Let me ask the audience if there is any more questions. I don't see any right now, so I'm going to start. I wanted to ask you about this reinforcement learning algorithm. Is the reward for the chaining, whether you decide to go diagonal, right, left, is it something that is like intuitively easy to explain? How do you decide this reward?
Yes. So basically what we have done is train the deep reinforcement learning algorithm in current maps like this one, in which we we cut this current map in blocks like this, and we have given a reward that it's higher, let's say, or a better reward to where the bias triangles are, and a very bad reward in places like, for example, here when there is no current or where there is a lot of current. So basically there is, we have tried different rewards, and but it's not, let's say, it's I don't remember exactly the numbers, but they are we gave something like -1 to all that it's bad, and +10 to the bias triangles or something like that. And we also penalized the algorithm when so when because sometimes it kind of it can do a lot of, let's say, it can do a lot of measurements without finding, so it can reach a maximum of blocks measured before stopping without fine triangles. And when it does happen, we give let's say, we punish the algorithm a lot for that. So when it measures a lot and finds nothing, that's the worst that can happen to this agent, basically.
Clear, thank you. The next question is from Steven. Please go ahead.
Hi, Natalia. Thank you for an interesting talk.
Yes,
In the superconducting qubit world that I'm used to, you're trying to do Hamiltonian calibration. You know, what if I send a pulse, what does it do?
yes.
And we face the problem of not just learning that, but in order to learn that, we have to know how our detectors work. And they also have to be calibrated. But to calibrate them, you have to do controlled operations on the qubits and see how the measurements change. So there's a kind of bootstrapping thing, which the experimentalists have kind of developed heuristic schemes for. But I wonder if you've thought about, you know, these kinds of questions.
Yes, indeed. So something that I'm really interested in, because, you know, I my thing are semiconductor devices, but I think most of the things in Oxford we have 2 labs that are very close by of superconducting qubits and ion traps, and interacting with them, we realize that many of the problems, like the one you just mentioned, are very similar to the problems we have, because once you have the, you know, qubit defined in these systems, you have to again optimize the pulses and learn the Hamiltonian, and again there is the instrumentation itself that has to be calibrated. So I'm pretty sure that all, you know, the things that we develop for one type of qubits might really be helpful for other qubit realizations, and this is the problem of kind of loop compensation. I think it's one that fits very well these machine learning approaches. I mean, in the case of superconducting qubits, the Hamiltonian, it's a lot clearer than in these semiconductor devices sometimes. So it is a bit easier for the machine learning in terms of understanding the pulse sequences, for example, than it would be in semiconductor qubits, the optimal pulse sequences, than it would be for semiconductor devices sometimes. But I think that this compensation and let's say iterative calibration, it is something we are super interested in. I mean, sometimes you realize that it's you can do it automatically without any very sophisticated algorithm. It's just a matter of thinking the problem and realizing that there are ways that kind of, you know, sometimes just a script can do it, but the superconducting community has been working on this for a long time, so I'm sure those are explored, and it would be very interesting to know what machine learning can bring to that picture.
Right. Thank you.
Thank you.
So we have a next question kind of from a chat from Angel. Can you unmute yourself and ask if you are still interested?
Yeah, can you hear me?
Yeah.
Yes.
Okay, so when you were talking before about making your measuring faster, you saw some Coulomb diamond shapes, and so if I understand well, your measurement is with a few only with a few points, and then you can reconstruct a more resolution image.
Yes.
Yeah, to do so, you train a neural network. But my question is, this training, do you do with a few points in the simulations, the same points that you are going to measure in your real experiment, or you do the? I mean, if you want to identify a low resolution measurement, then your training should be with the same resolution.
Yeah, I agree. No, so let's say we take a low resolution measurement, and that we use. In principle, you wouldn't need it, right? We agree. We agree that in principle we could leave the algorithm start with, you know, some reconstructions that it comes up with. So in principle, you know, we can start with the reconstruction, do the first measurement, and then get basically, and then get the then update those reconstructions, and then in principle the reconstructions will look nothing like the real measurement, but then, you know, these continue update of reconstructions would make well, would kind of make the reconstructions look a lot like the real measurement. So in principle, this initial scan is not necessary. Why do we have it? Well, we have it to actually make the reconstructions a lot less fuzzy. What happens is that, you know, they are a bit like, they allow us to actually make our reconstructions sharper. And this is what we have observed in our in our training. And that's why we do need this low resolution measurement first, because it helps a lot the reconstructions, but basically that's it. But in principle, it's not necessary.
Okay. Thank you.
Thank you.
Next question is from Anton.
Thank you. Thanks again for the talk. I have one very overarching question. Your diagram with all the different components suggested that you start from the coarse grained and end up with the tuning. But of course, the references on all of these are different. So do you have like a single device where you manage to run the complete thing as a pipeline?
We haven't tried yet, but that's indeed something we are, because, you know, we started with problems and as you say, we haven't started in order. So, but that's, you know, we, for example, for both these the deep reinforcement learning and the fine tuning here, we use this one to kind of find the double dots. So we do use them now all the time, because they're the easier way of doing it. Sometimes when we have, you know, very long measurements, we use these. So we use them in the lab, but it's not that we have said, okay, now let's demonstrate them all together. That we haven't done, but I mean, it would be cool to do it, and certainly we should. But yeah, we kind of now we use certainly the super coarse tuning routinely. I mean, we don't do it by hand anymore. It's just yeah, it just always works. And we have seen in many different devices, even, you know, for the thermodynamics, we work with carbon nanotubes, and you throw it to carbon nanotubes and it works, because it doesn't really matter, you know, for the algorithm, but what you're actually what if it's a carbon nanotube or a gallium arsenide structure or whatever it is, it just works. So that's really nice. And this is also why, in some sense, the classical machine learning, it's really powerful, because it depends a lot less in training. And depending a lot less in training means that it's a lot more applicable to different types of devices. So it kind of that's something that we that of course then it's very powerful, because then you throw it to almost any device and it just works.
Thanks.
Okay, so to me this sounds like this was a good overarching perspective to finish on. I will give one last second to if anyone wants to raise the hand for one short last question. I don't see any. So with that, Natalia, thank you again. This was really great talk and awesome discussion. And thanks everyone for coming and listening. And we will see you in 2 weeks.
Thank you all. Thank you, Eliska.